And the basic idea is, again, quite simple. The brain is locked inside its bony skull. It has very indirect access to the external world. All it receives are ambiguous and noisy sensory signals, which are highly indirectly related to this external world of objects and so on, if there is an external world of objects out there at all. Don't know about that. Perception in this view is by necessity a process of inference in which the brain interprets these ambiguous and noisy sensory signals with respect to some prior expectations or beliefs about the way the world is. And this forms the brain's best guess of the causes of the sensory signals that are impacting our sensory surfaces all the time. What we see is the brain's best guess of what's out there. I want to give you a couple of examples that illustrate this process. It's quite easy to do in a way. This first example is a well-known visual illusion called Adelson's checkerboard. Now here, you'll see two patches. You'll see patches A and B. And I hope to you they look to be different shades of grey. Do they? Yeah, they look to be different shades of grey. Of course, they are exactly the same shade of grey. I can illustrate that by putting an alternative image and joining up those two patches. You'll see that it's the same shade of grey. You may not believe me, so what I'll do is I'll shift it along and you'll see even more clearly. There are no sharp edges, it's the same shade of grey. What's going on here, of course, is that the brain is unconsciously applying its prior knowledge that a cast shadow dims the appearance of surfaces that it casts onto. So we therefore see the patch B as being lighter than it really is in order to account for that effect. And this is, of course, an illustration of the success of the visual system, not its failure. The visual system is a very bad physical light meter, but that's not what it's supposed to do. It's supposed to, or one thing it's supposed to do, is to interpret the causes of sensory signals in terms of meaningful objects in the world. It's also an example of what we sometimes call cognitive impenetrability. Even if you know the patches are the same shade of grey, when I take that bar away, they again look different. So, can't do much about that. The second example just shows you how quickly the brain can take in new prior information to change the nature of conscious perception. This is a so-called Mooney image. And if you haven't seen it before, hopefully what you will see here, it's just a pattern of black and white splodges. Does everybody kind of get that? Black and white splodges? Yeah, some of you might have seen this before. And now what I'm going to do is fill it in, and you'll see something very different. What you'll see is a very meaningful scene here involving at least two objects, a woman, a hat, and a horse. Now, if you stare at this for a while, I won't leave it up for too long, but if you just look at it for a little bit, and then I take that image away again, you should still be able to see the objects within that image. Now, for me, this is quite remarkable because the sensory information hasn't changed at all. All that's changed are your brain's prior expectations about what that sensory data signifies, and this changes what you consciously see. Now, this also works in the auditory domain. Here are two spectrograms. This is something called sine wave speech, and what you see here are two time-frequency representations of speech sounds. The one on the top has all the sharp acoustical features that pervade normal speech removed, a little bit like thresholding an image. And the bottom is something else. So I'm going to play you the top first, and let's see what it sounds like.
Jazz and swing fans like fast music. Jazz and swing fans like fast music.
And now I'll play you something else.
Jazz and swing fans like fast music.
So I hope you all understood that piece of sage advice. And now if I play the original sound again.
Jazz and swing fans like fast music.
Yeah? So it's exactly the same. Again, all that's changed is what we expect that sound to signify. One more time, just for that.
Like fast music.
It's not just a bunch of noisy whistles, it's speech. Now, this typical framework for thinking about these kinds of effects is Bayesian inference. And this is a form of probabilistic reasoning, which is applicable in all sorts of domains, not just in neuroscience, in medical diagnosis, all sorts of things, finding lost submarines. But in neuroscience, we talk about the Bayesian brain, and it's a way of formalizing Helmholtz's idea that perception is a form of best guessing. And the idea is that sensory signals and prior beliefs can be represented as probability distributions. So for instance, this yellow curve is the probability of something being the case, maybe that you've got a brief glimpse of an object moving to the right. The sensory data may say something different. It may have a probability that peaks at a different angle of movement. Maybe it's drifting in a different direction. And the optimal combination of the prior and the likelihood, the yellow curve and the red curve, is this green curve, which we would call the posterior distribution. And that represents the best optimal combination of these two sorts of evidence. And the idea is, well, that's what we perceive. Thinking about perception in this way does something rather strange to the way classically in neuroscience people have thought about perception. The classical view is that the brain processes sensory information in a bottom-up or feed-forward direction. So this is a picture of the visual system of the monkey, and the idea is that information comes in through the retina, it then goes through the thalamus, it then goes to the back of the brain, and as the sensory signals percolate deeper and deeper and deeper into the brain, they encode or represent progressively more sophisticated features of objects. So you start out at early levels of visual cortex with response to luminance and edges, and then higher up to objects, including other monkeys. What's important here is that the perceptual heavy lifting is done by information flowing in this bottom-up or feed-forward direction. Now, the Bayesian brain idea says something very different. It says that what's really important are the top-down or inside-out connections that flow from the center of the brain back out. And we've known for a long time there's a large number, very large number of these connections, and some descriptions more than flow the other way around. But their function has been rather mysterious. Thinking about the Bayesian brain gives us a nice way to interpret this, which is that it's exactly these top-down or inside-out connections that convey predictions from high levels of the brain to lower levels, back out to the sensory surfaces. So these blue arrows convey the brain's predictions about the causes of sensory signals. And then what flows in the feed-forward or bottom-up direction from the outside in, that's just the prediction error, the difference between what the brain expects and what it gets at each level of description. So this is often called predictive coding or predictive processing in some formal frameworks. And the idea is that minimization of prediction error then occurs across all levels of this hierarchy at the same time, and what we then perceive is the consequence of this joint minimization of prediction error. So you can think of perception as a sort of controlled hallucination in which our perceptual predictions are being reined in at all points by sensory information from the world and the body. Now, there's quite a lot of experiments that show that something like this is probably going on in the brain. These are a couple of examples, and since they're, I was looking for the best examples, so they don't come from my lab at all. This is from Lars Muckley in Glasgow, and he's shown using advanced brain reading techniques, which I won't describe, that you can decode the context of what a person is seeing from part of the visual cortex that isn't even receiving any input. And what's more, you can decode better when you decode from the top part of the cortex, which is supposed to receive predictions from higher levels. So that suggests there are predictions being fed back. In another study by André Bastos and Pascal Fries in Germany, they used a method called Granger causality, which is sensitive to information flow in systems. And they find that top-down signals and bottom-up signals are conveyed in different frequency bands in the cortex, which is what you'd predict from predictive coding. One last experiment which I find particularly interesting is this is in an experiment from a Japanese group of Masanori Murayama, and they used optogenetics, which is a way of using light to selectively turn on or off neural circuits. And in this experiment, they showed that by just deactivating top superficial levels of somatosensory cortex in a mouse brain, the part of the mouse brain that's sensitive to touch, they could affect how well that mouse was able to do tactile discriminations. And those top-down connections were coming from motor cortex. So there's a lot of evidence that top-down connections in the brain are important for perception, is the basic message there. But what's rather strange, and what I'm going to tell you next, is that All this stuff is all very good, but predictive processing is not a theory of consciousness. Nothing I've said has anything to do with consciousness at all. It's a very general theory of how brains do what they do, how they do perception, how they do cognition, how they do action. So somewhat counterintuitively, I think this is exactly why it's a great theory of consciousness.
Hello, I'm Allison. I have read a lot about neuroscience since 2003 and is fond of it. In 2016, I discovered a great novel on neuroscience, the unique book I'd like to share with you on this channel here for 3 reasons. 1. It shows you an original approach to neuroscience that has been never done before. 2. It's quite well written, you're totally captivating. That's an amazing thriller. And 3. It is based on a serious and true study about electromagnetic harassment. I highly recommend you this book entitled Neuroscience, Crime and Corruption, White Mind Distortion for 2 main reasons. 1. It deals with neuroscience in a totally different way as usual. The innovative form used is a novel. And I'm pretty sure that you have never ever read a novel about neuroscience, but articles and studies. The second reason is the quality of the book. Well, it's pretty good written and the story is captivating. You can click on the link here to know more about the story, which is a thriller. What I can tell you is I couldn't help myself reading when I started. I was so in. The characters are incredibly amazing, and the story is so unbelievable. What an experience. So if you want to know more about this book, and I think I'm gonna make more videos like this, just click here. Thank you for watching. Don't forget to like and share this video. Bye.